Hello class, I'm going to walk through the solutions here for week 7. On question 1, we had Amy, Bill, and Cade leaving point A and walking towards point B. They leave at different times, but all arrive at point B at the same time. That suggests that they are walking at different speeds, but that really doesn't matter. All we have to know is when each person left and when they all arrived at point B. And we know that this timeline here is especially helpful. We know that Amy left, and 20 seconds later, Bill left, and then 10 seconds after Bill left, Cade left, and they all finished 70 seconds after Bill. After Bill started his journey, I should say. They all finished 70 seconds after Bill started. So this tells me that if I use the frame of reference 1, where Amy is left at what we're calling time 0, then Bill left at time 20 seconds, that is. Cade left at time 30, and they all finished 70 seconds after Bill left. So we'd have to go from 20 and add 70 to get 90. And then if we just change our frame of reference to the different starting times being time 0, and then when they finish it being time 0. In timeline 2, we're saying Bill left at time 0, so Cade would have left at time 10, because it's 10 seconds later, and Amy would have left at time -20, because it's 20 seconds before Bill left. And then they finished 70 seconds after Bill left, so they finished at time 70 in this frame of reference. In the next frame of reference, we're saying that Cade left at time 0. So that means that Amy left 30 seconds before Cade, so she's time -30. Bill would be time -10, and they would have finished at time 60. Right, 60 seconds after Cade left, or 70 seconds after Bill left. And then finally, in the last frame of reference, if they finish at time 0, then Amy started 90 seconds before, so she's at time -90. Bill started 70 seconds before that, so he's at time -70. And Cade was 10 seconds later of Bill, so that's at time -60. Let's go to the next one, question 2. We're adding 3 and 5 using integer chips. I'm using green dots for pluses and red dots for minuses. Here's the 3, and combine that with 5, and that just makes a total of 8. Pretty easy to model. If you're doing the number line approach, then you start at 3, and then you add 5, so you go 5 to the right, and that takes you to 8. If I combine 4 negatives with 7 negatives, I get just more negatives, if you will. I'll get -11. And when you add a negative number, you go left on the number line. So we started at -4, and I add -7, so go 7 left on the number line, and that takes you to -11. Now when I combine some negatives and some positives, we're going to get some cancellations. So here's the 2 negatives, combining that with the 7 positives. And that's actually, 9 positives, adding 9 positives to that. Not 7, I don't know why I said 7. The answer is going to be 7. But these 2 reds and these 2 greens combine to make 0, so they just cancel each other, leaving you with just 7 left. And on a number line, you would start at -2, add 9, which means go to the right 9 units, and that would take you to 7. And then finally, we're combining 6 positives with 11 negatives, and then these 12 chips here cancel. 6 positives and 6 negatives cancel, leaving just these 5 negatives left, so the result is going to be -5. And on a number line, we start at 6, and if I add a negative number, I go left 11 units, and that takes me to the result of -5. Then to identify any patterns, we've noticed that if we add 2 positives, we make it even more positive. So adding 2 positives produces a number that's even further to the right on the number line. But adding 2 negatives makes more negative. It goes further left on the number line. And adding a positive and negative will cause some zeros, and it can result in a positive or negative result depending on whether there were more positives or more negatives to begin with. Like in this case here, we had more positives than negatives to begin with, so we wound up with having positives after the cancellation happened, whereas in this case we had more negatives than positives to begin with, and so after the cancellation we wound up with some negatives still left over. You might have seen some rules like if they're the same sign or opposite sign, like 6 and -11, then just subtract 11 and 6, so get 5, but then keep the sign of the larger number. You might have heard a rule like that, but I don't like teaching those rules because rules without a proper foundation can often not make sense to a student. They just memorize what in their thinking is just gibberish. Number 3, can draw a depiction using integer chips to perform the following operations. So we're going to do the takeaway model for subtraction. So we're going to do 3 minus 5, 3 take away 5. So I begin with a depiction of what 3 looks like, but then I realize that there aren't 5 greens that I could even take away. So I'm going to alter the way 3 looks like by adding a few zeros, and I needed to add 2 more zeros to get the 2 more greens. So even though there's some reds and greens here, I mean, this represents the value of 3, because what's in the pink box equals 0. But now I'm in a position where I can take away these 5 greens, and that would then leave 2 reds left over. So doing 3 and take away 5 would take you to -2. If I have -4 and I want to take away -7, well, I start with a representation of -4, but there aren't 7 reds to take away, so I need to add 3 more zeros. And now I can see that I have 7 reds I can take away, and that leaves these 3 greens left over. So -4 take away -7 will result in +3. Here's -2 take away 6. So I start with -2, and I need to take away 6 greens, where there are no greens. So I have to add 6 greens and 6 reds. So I add 6 zeros. So this, expression, or this value right here is still -2. So we're starting with -2, but with a bunch of zeros added to it. And we're going to take away now these 6 greens, and that leaves left over these 8 reds. So the result of -2 take away 6 is -8. And finally, 6 take away -5. Well, here's 6. Well, there's no reds to take away, so I need to add them. And now I'm in a position where I can take away 5 reds, and that leaves, if I start with 6 and take away 5 reds, I wind up with 11 green dots, so 11. Explain why subtracting a positive integer is equivalent to adding the opposite. Well, removing greens is equivalent to adding reds to cancel those greens. For example, if you start with 4 greens and I say take away 3, then that's really the same thing as starting with 4 greens and adding -3. Because the end result will be, right, if I take those 3 away, then I'm left with just 1. But if I add 3 reds to those 3 greens, they cancel, and you're also just left with that 1. So either way of thinking about this has the same effect, removing greens or throwing reds in there to cancel those greens. And similar for the other direction, removing reds is equivalent to adding greens to cancel those reds. So if I had 4 reds and I wanted to remove 3 of them, then I could. Or I could just add 3 greens to the 4 reds so that the net effect is canceling 3 of those reds. And either way you think about this, you're left with a single red in this example here. If you want to think in terms of, money, taking away money is like adding debts, and taking away debts is like adding credits. Something to think about. Something the kids might be able to think about, and that would make sense to them. Number 4, draw a depiction using integer chips or doing subtraction, but this is the comparison model. So when I say 3 minus 5, that means what do you need to add to 5 to make 3? Right, this is going to produce a negative answer, but think of a case where you don't get a negative answer with like 6 minus 4. We know the answer is 2. It's because we're answering the question, if you started with 4, what would you need to add to it so to make 6? And that's called the difference, and that's how you find a difference. So we're doing this now just with negative numbers present. So if you see 3 minus 5, I'm thinking, okay, what do I need to add to 5 in order to make 3? So I start with 5, and I want to add stuff to that so that the result is 3. Well, the net effect is to get rid of 2 of these greens right there, get rid of those, and that's how you can get 3. But I have to ask myself, what do I add to 5 to make 3? Well, you want to add 2 reds. So once you answer that question, when you add these 2 reds, right, and you put them there, it cancels those greens. That's just one way to remove 2 greens, is to add 2 reds. So the end result, then, since we answered the question, answer the question is -2, so therefore 3 minus 5 is -2. Here's -4 minus -7. So again, what should be added to -7 to make -4? Well, here's -7. I want to produce -4, so I need to add these 3 greens to it, so that those 3 reds will cancel, leaving just those 4 reds. And so the answer to this is a +3. 3 is what needs to be added to -4 to make, 3 is what needs to be added to negative 7 to make negative 4. And then here we use the number line approach to do subtraction. We start with the minuend, so we start here at negative 2, and then when you subtract a positive, you go left. So we go left 6 units to get to negative 8. And then if you subtract a negative, all right, we start with the minuend, so start at 6, and then if you subtract a negative, we go right. We go right 5 units to get to 11. You'll notice that these 4 problems were the same 4 problems over here, just using different models. Here we did takeaway models to do all 4, and then I did 2 of them using the compare model, and then 2 of them using a number line approach. Then without using integer chips, well, you can use integer chips, you just didn't need to show that you were using them, really is what I meant to say there. Here we're going to be doing subtraction of a sum or difference. And we're going to do this in 2 ways. One is to handle what's inside the parentheses first. So do 2 plus negative 5, that will add to negative 3. And then do 7 take away negative 3, that's the same thing as doing 7 and add 3, and you get 10. Where over here, we're going to see if we're going to distribute the subtraction and say we're going to do 7 take away 2, and then take away negative 5. And go in this order, and now just go from left to right. So do 7 take away 2, gives you 5, and then do 5 take away negative 5, that's the same thing as 5 adding 5, and that gives you to 10. So what we're seeing here is that the distributive property of subtraction holds even if we're working with integers. We had already demonstrated that it held when I worked with nothing but whole numbers, so no negative numbers, but we're seeing that it still holds even if negative numbers are involved. Here's some multiplication. 5 times negative 3, that just means do 5 copies of negative 3. So here's your 5 copies of negative 3. Combine them together and you get negative 15. But when your multiplier is negative, we have this idea of removing. So when you see negative 4, then think you want to remove 4 copies of negative 2. And what are we removing from? Well, let's start with 0. Let's start with nothing and then remove 4 copies of negative 2 and see what we get. So I started with a depiction of 0 as 8 0 plus minus 0 pairings. So this is 0, but it's a representation of 0 that will allow me to remove 4 copies of negative 2. And when I remove these 8 reds, essentially, you're left with positive 8. Here it's remove 3 copies of 5. Well, I start with a 0 that has 15 0 pairs in there, and then I remove the 3 copies of 5. And that leaves me with essentially 3 copies of negative 5, and that's negative 15 value. And then here, if I multiply a negative times a negative, if I remove 2 copies of negative 4 from 0, so here's our version of 0, and I'm going to remove 2 copies of negative 4, and that was going to leave me a result of positive 8. Notice that what you're seeing here I did 5 times negative 3, combine 5 copies of negative 3, and here's where I said, hey, remove 3 copies of positive 5, and the end result was negative 15 in both cases. And here I removed 4 copies of negative 2, and here I removed 2 copies of negative 4, and the result is 8 in both cases. So this is suggesting that integer multiplication appears to be commutative. And it is a commutative operation even with integers. And also we notice that if you multiply 2 positives, if you combine groups of positives, then you get more positives. So the result is positive. If you multiply 2 negatives, if you remove negatives, you get positive. And if you remove groups of negatives, you get a positive result. But if you multiply a positive and a negative, you get a negative result. For example, if you combine negatives, you get a negative, and if you remove positives, you get a negative. So either way, when you multiply a positive and a negative, no matter which one is the multiplier or multiplicand, you get a negative product. Number 6, we're going to just illustrate that distributive property holds. So here we're doing method 1 is to do what's in the parentheses first. So negative 3 plus 8 is going to be positive 5, and then just do negative 2 times 5. So remove 2 copies of 5, that's going to lead to negative 10. And here we do the distributive property. So I'm going to distribute the negative 2 to both parts of this sum and see what happens. So we do -2 times -3 and then add -2 times 8. Well, remove 2 copies of -3 makes +6. Remove 2 copies of 8 leads to -16, and combining 6 and -16 makes -10. So notice we get the same result this way if I distribute first. And when I say same result, we're comparing method 1 and method 2. Same result. Here, do inside the parentheses first. You get -3. 4 take away 7 is going to give you -3. And then remove 5 copies of -3. You get 15. And 4 minus 7, or here we're going to do distributive property first. So we're going to do -5 times 4 and then minus -5 times 7. So we have -5 times 4. Remove 5 copies of 4 gives you -20. And then here's remove 5 copies of 7 will give you -35. But now I'm going to subtract -35. So that's like adding 35. And so we do -20 plus 35. That leads to 15. Right? Same result as we get using method 1. And here we do inside the parentheses 1 minus -9. 1 take away -9 will be like 1 add 9, and we get 10 total. And then 4 copies of 10 combined to make 40. And here distribute first. 4 copies of 1 make 4. And 4 copies of -9 make -36. But remove -36 is the same thing as adding 36 to this 4, and you get 40 this way as well. So all the results for method 1 and method 2 are the same. It seems like method 1 was simpler as far as how much writing we had to do, but other than that, it doesn't really matter which way you do this. The distributive property for multiplication holds even for integers. And finally, the division. Now this one gets a little bit trickier because a negative multiplier means to remove copies of something, but a positive multiplier means to combine copies of something. And let's walk through all the partitive meanings first. Knowing what the correct question to ask is super important. So when I see -10 divided by 5, I ask myself the following question. This is partitive, so 5 is the number of copies. So in other words, we're trying to find a multiplicand. This is a missing multiplicand task. So I'm asking myself 5 copies of what will combine to make -10? Well, I start with a representation of -10, and then I can see that there's 5 copies of -2 will combine to make -10. So the answer to this is -2. 5 copies of what? The answer is 5 copies of -2 will make -10. Therefore, using a partitive meaning, -10 divided by 5 is -2. Let's just do all the partitive meanings. Here, when I'm dividing by -3, that's a multiplier. We're trying to find a multiplicand. And because the multiplier is negative, we want to think removing from 0. So the question becomes, we're going to remove 3 copies. Oops. Right, remove 3 copies is what a -3 multiplier does. Remove 3 copies of what to make 12? Well, I'm going to start with 0. Or here's the result. I want to produce 12. And so I'm going to start with a 0 that has 12 greens and 12 reds. And then I can see that how many copies of what need to be removed. Well, if I remove the 3 copies of the -4, that will yield +12. Therefore, 12 divided by -3 is -4 by the partitive meaning for division. And similarly here, we have a negative multiplier again, right there. So we're saying remove 6 copies, because we have a negative multiplier. Remove 6 copies of what to make -18? Well, -18 is 18 reds, so I'm going to start with 18 0 pairs. And I can see that I want to remove the greens to make a red, and I need to remove 6 copies of 3. That will produce a -18. Therefore, the answer to this division is 3. Now, the same problems are going to do both quotative meanings, so the question changes. It's now quotative is for a missing multiplier, and since the multiplier is unknown, I don't know if it's positive or negative, so I don't know initially if I should be combining or removing. So we just have to think through that a little bit. But the general question when you're doing quotative meaning with negative numbers, with integers, is, so 5 is what's being copied, and we're trying to make -10. Well, you can't combine copies of 5 and make a negative number. So you're going to have to remove copies of 5 to make a negative number. So that tells me that of the 2 options, I need to get rid of combined and go with the removed thinking. So right away, because I know that I need to remove copies of 5 to make -10, that my multiplier is going to be negative. So the actual whole question here, though, is now phrased this way. How many copies of 5 need to be removed to make negative 10? Well, negative 10 is 10 reds, so I start with 10 reds and 10 greens, which is 0, and I see that if I remove 2 copies of 5, remove those greens, I'll get the 10 reds. So the answer to this is negative 2, suggesting we remove 2 copies of 5 in order to make negative 10. Now compare that to the partitive meaning. They're very different ways to think about division, yet they both yield the same numerical result. It's just the way we imagine what division means is different, but the numerical result is negative 2 in both cases. Here we have 12 divided by negative 3, so this is the multiplicand. I don't know the multiplier, but if I combine copies of negative 3, I'm going to get negative result. But I'm trying to combine copies, I need to remove copies of negative 3 in order to yield a positive result. So again, the question is, we get rid of combined and we go with removed. And the question now is, how many copies of negative 3 need to be removed to make 12? Well, here's 12. It's 12 greens. I start with 12 greens and 12 reds, which is 0, and I ask myself if I need to remove remove how many copies of negative 3. I can see if I remove 4 copies of negative 3, then that will give me the answer. So the answer, our multiplier, is negative 4. The negative suggesting we're removing 4 copies of negative 3, and that will yield 12. And finally, negative 18 divided by negative 6. So how many copies of negative 6 need to be, well, if I'm starting with a negative amount, then I just need to copy it to stay a negative amount. So I don't need to remove copies of negative 6, I need to combine them. So the question is, how many copies of negative 6 need to be combined to make negative 18? Well, here's negative 18, and you can see that if you combine 3 copies of negative 6, you'll get negative 18. So the answer to this is 3, suggesting that combine 3 copies of negative 6 and you will get negative 18. Similarly, like for multiplication, we're seeing that when I divide 2 positives, which is not depicted in your assignment, but when you divide a positive by a positive, you get a positive back. When you do a negative divided by a positive, you get a negative back. We saw that with this example and this example, no matter which way of thinking for division you did. And when you divide 2 negatives, we yield a positive, right? No matter which way of thinking you did, you yield a positive. So the rules for multiplication and division are similar as far as what sign to expect, depending on what signs you're operating with. And if you divide 2 positives, you get a positive. If you divide 2 negatives, you get also a positive. But if you divide a positive and a negative in either order, divisor and dividend, doesn't matter which one is which, but you get a negative quotient. Okay, and that's it for this homework assignment.